Hi, this is Yanofsky. This is the class's analysis of algorithms. We're doing chapter 4, divide and conquer. So let's just recap what we're doing, what we did before. So chapters 1, 2, and 3 was the mathematical background. This chapter is like a little interlude, and all it's about is recursion, because we're going to use recursion for the rest of the semester. Every single algorithm, a lot of algorithms are going to be recursive, and so we want to get a feel for that. Okay, so recursion has this feel of as follows. You have a problem, you divide the problem into little parts, you conquer the little parts, and then you bring it together, and you solve the larger problem. So again, you have a large problem, you chop it up into little problems, and you solve the problem. It's the right way of programming. It's really nice, etc., etc. But students find it hard, which is okay. Okay. Now, in regular programming, we said you get a function like that, which you compare to. Okay? But in recursive programming, you don't get that. Okay? Instead, what you get is something called a recurrence relation. Okay? Something like this. T of n is equal to 15 t of n over 3 plus n squared. Okay? See, now that is not a function. You have an input of t of n, and you get back something t of n over 3. It's very hard to calculate these, okay? But this is what recursion is all about. It says if you want to solve this big problem with n inputs, you solve it this way with n over 3 inputs. You chop the problem into smaller pieces, and you're able to do that. Okay, the problem is we don't like recurrence relations. Okay, and so what we're going to do the second half of this chapter 4 is change recurrence relations and get out functions, because we like functions. Functions are easy to do, etc., etc. Okay, let's start off with some examples of recursion that we already know. Okay, so again, just baby examples of recursion. The first example you saw of recursion is probably Fibonacci series. Fibonacci of n is equal to Fibonacci of n minus 1 plus Fibonacci of n minus 2. And the boundary conditions are Fibonacci of 1 is equal to Fibonacci of 2. You start off with both of them equaling 1. Okay, a more interesting example, again, probably that you programmed the first semester in computers, is the factorial. So this is n factorial, and it's defined as n times n minus 1 factorial. Okay? And again, factorial of 1 is equal to 1. So 7 factorial is equal to 7 times 6 factorial. Okay, and what's 6 factorial? Well, that's equal to 7 times 6 times 5 factorial. Okay, and this goes on until you get 7 times 6 times 5 times 4 times 3 times 2 times 1 factorial, which is 1. Okay, so, but again, what you see is, in order to solve a big problem, n, you have to solve n minus 1. Okay, that's typical. Let's talk about something also you probably saw in first semester programming. Okay, but again, we'll bring in here as an example of recursion. Okay, if you do a binary search, okay, you have a giant array, and you want to, and the array is ordered, and you want to search for somebody. Okay, and the idea to keep in your head is you're looking in the Brooklyn telephone book for some particular person. And so what you do, you don't start at the beginning of the telephone book and go through the pages one by one. What you do is you take the telephone book, you split it in half, you look at in between for that name, and you see, do I go this way or do I go that way? Okay, and then you keep on splitting the telephone book more and more until you get smaller and smaller parts. Again, each time you do one operation and then you split it. One operation and you split what's remaining. One operation and you split what's remaining. Okay, the recurrence formula that goes for that is this. T of n, if I have n elements in my array, how many operations do I have to do to find one of them? Again, the array is ordered. Well, the answer is I do one comparison because I want to know, do I go to the left or do I go to the right? Do I move up or do I move down? And once I do that one comparison, I still have to look at half of the results left. Okay, so that's the recurrence formula for the binary search algorithm. Okay, you might have boundary conditions like this. If you have one object, so then you have one comparison more. Okay, now we would like to solve this, and I'll tell you what it is. Okay, if you remember what we said about logarithms, logarithms base 2 tells you how many times you can split a number into 2. Split it, split it, split it. Divided by 2, divided by 2, divided by 2. As opposed to exponentiation, which tells you how many times you multiply something by 2, here is how many times you divide by 2. Okay? And every time you divide by 2, you add 1. So what is this? What is the function that corresponds to this recurrence formula? And the answer is T of n is equal to log base 2 of n. Every time you split it, you add 1. We're looking how many times you add 1. That's the logarithm. Okay? Okay. Let's just do one more that we did this semester. In the beginning, chapter 1, I think, or chapter 2. Okay? And that was merge sort. Okay? And in merge sort, what we said, if you want to sort an entire list, then what do you have to do? You have to sort the left half plus sort the right half plus merge them together. And we said merging them together is an array operation. Okay? We shorten this to, and by the way, here you see the divide and conquer. You have a giant list. You divide the list into 2, and you conquer each one, and then you bring them together. Okay? You shorten this to t, 2t, n over 2 plus n. Okay? And one of the things I said, and we'll actually see it later at the end of this chapter, is that this recurrence formula corresponds to T of n is equal to n log base 2 of n. Okay, so those were 4 baby examples of recursion, and now what we're going to do is a whole section which really gets into the nitty-gritty details of recursion. We're going to do two examples of them. Okay, so first we're going to start with section 4.1. We're going to do section 4.1 and 4.2, which does 2 nice big examples of recursion. 2 technical details. Notice when I wrote down for merge sort and when I wrote down for merge sort, I didn't write the boundary conditions. So the boundary conditions we're going to just take as 1. In other words, when you have small inputs, it's going to be 1 or 2 or 10. It's going to be a constant. We don't really care about that. Okay? So we're not really going to worry about, whenever we write a recurrence formula, we're not really going to worry about the boundary condition. And the other thing is, following the book, we ignore floors and ceilings. Okay? Sometimes the book gets into it and they go through it more clearly and more carefully, but we're going to be a little bit sloppy with it, hand wavy, and say, you know, okay, I don't care if it's odd or even, floors or ceilings and stuff like that. So we're gonna not worry about that. Okay, so let's start with section 4.1. It's called the maximal subarray problem. Okay. That was our introduction to recursion. So let's do section 4.1, the maximal subarray problem. Give me a little time to get to the problem in general, but let me explain to you what it's all about. Okay? So let's say I go to the future. I go to the past, go to the future in my time machine, and I get next month's stocks, the prices for next month's stocks delivered. In other words, I'm given an array, and the array tells me at every point when to buy and when what's the price of the stock. So I have 30 numbers going up and down telling me what the price of the stock is. Okay? And what I'd like to do is I'm allowed to invest once in the next month, and I'd like to make the investment that wins the most money, that gets the most money. Okay? So how do we solve this problem? We're going to go through it 3 different ways. Okay? The first stab is as follows. Okay? We find the minimum, go through the array, find the minimum, find the maximum, and you're done. Okay? In other words, find that when it's cheapest, buy it at its cheapest price, find when it's the most expensive, sell it when it's the most expensive, and you made the most money. Okay? In stocks, that's called the spread, the maximum spread of the things. Okay? The problem is that that's not always true. For example, consider the following. Consider the following sequence of numbers. Okay? Here, the minimum is here. The maximum is before that. So that's not going to work. Okay? You're not going to be able to do that. Okay? You're not going to make a lot of money if you can't buy here and sell here. That doesn't make sense. Time goes this way. Okay, so that doesn't work. Let's do it a better way. Okay? Let's take this problem and do it a better way. Okay? One is, so this is the second way. This is the second stab at the problem. Okay? Find the minimum. Find when to buy it. Find maximum after minimum. Okay? You should also find the global max and find the minimum before that. Okay, so that after that, before max. In other words, okay, here's the global min. Here's the global max afterwards. That's good. Here's the global max afterwards. Here's the global max. Here's the min beforehand. Okay? Well, you know what? Just to make it more interesting, let's say this is the min beforehand. Okay? Okay? And so the question is, should I buy it here and sell it here, or should I buy it here and sell it here? Okay? Okay. That's a second thing that you might want to do. Let me just show you why this doesn't work either. Okay? I made up a nice little example where this doesn't work. Okay? So here's a nice example. Let's say your stock is at 10. It goes up to 12. It goes down to 7. Goes up to 10. Goes down to 6, and goes up to 7. Okay? Okay, so let's do this algorithm. Okay? I find the min, the global min is here. okay, and the max afterward is over here. So this is the first thing to do. Okay, this is the first thing to do. So we'll call this A. So this is the A. This tells you by this. Okay, as opposed to that, we find the max, which is 12. Find the min before max. That's that. Okay, so this is B. So we do this. Here we'd make $1. Here we would make $2. But what's the real answer? What should you really do? You should not look at the global min, nor should you look at the global max. What you should really do is this. C. Okay, you should really do this. This is what you should really do. So this algorithm doesn't work because even if you look at these two things, you'd get a different answer from that. The real answer is different from that. Here you make $3, here you make $2, here you make $1. So that doesn't work. Okay, great. Okay, so we have to adjust. We have to find a third way of doing it. Okay, and the third way of doing it is still not the right way, but we're going to say it out loud. The third way is as follows. You do a brute force search. You search through all possibilities. Every single day, you try to buy it, go through all possibilities of buying it, and all possibilities of selling it, and find the best possibility that you have. Okay? This is called a brute force search. You just, look, I have 30 days that I can buy it. I have 30 days I can sell it. Not really, because you have to sell it after you buy it. Okay? So you have 30 days that you can buy it. You look every day afterwards when you should sell it. Go through all those possibilities and see how much you should do. Okay? Find your best one. Now, I've taught this before, and I find students have trouble doing this. Okay, so I just want to go through the algorithm and actually do it. Okay. Okay, so here, the algorithm's not in the book, but we should do it anyways. Find max spread. Okay. You're given A, an array of numbers. Okay. And n, the number of elements in the array. I told you you have 30 elements in the array, and you're dealing with stocks, but we're not, you know, let's say you're given a whole year or something like that. You're given an array of numbers, and you want to find what's the best place to sell, buy a certain thing, and sell it afterwards. Okay, so we do it as follows. Max spread equals negative infinity. Okay, that means it's going to pick up the first possibility. Okay, and then here we do it. Ready? For I equal 1 to n. Go through the array. This is going to be your starting point of going through the array. Okay, for j is equal to 1 to, I plus 1. Okay, in other words, here's when you're buying it. You can sell it the next day. We don't do minute stocks, we do day stocks. Okay, I plus 1. Okay, this should be an n minus 1 because you can't buy it the last day. You have to buy it the day before the last day. Okay, 2n. And then we do the following. If a of j minus a of I. Okay, let's just go through what that is. I is when you buy it, j is when you sell it. This is the price when you sell it minus you buying it, okay, is greater than max spread. Okay, that started off as negative infinity, which means the first time you do it, you're definitely you're gonna pick that up. Okay, so if it's better to do it here than max spread. Okay, in other words, you're searching for your max spread. If you found something you thought was max spread already, but now you got something that's even better, the selling minus the buying is even better, okay, then max spread is equal to a of j minus a of I, In other words, if this selling minus buying is better than the previous max spread, you better make this one your max spread. Okay? And then we say we have to keep the results of what to do, not only how much money you're going to make, but what to do. So buy is equal to I, sell is equal to J. Close bracket. That's it. Okay? Now, this goes through all possibilities. This goes through all possibilities, and so you're going to find the absolute best answer. Problem, how much work is done. Okay? So let's just deal with it. Okay? You're going to do, the first time you're going to do n operations, or n minus 1. Okay? The second time you're going to do n minus 2. You're going to start I is equal to 2, you're going to do n minus 2. The third time you're going to do n minus 3 plus plus 1. Plus 3, plus 2, plus 1. Anyways, that's about, well, it's about n squared divided by 2. Okay, but it's theta of n squared. It's theta of n squared. Okay? So, yes, brute force search works, but not well. Okay? Can we do better? And the answer is yes, we can, but we have to do it recursively. Okay? So, let's set up the problem a little bit different. Okay, that's a nice algorithm, by the way. Rather than looking through all possibilities like that, let's see if we can figure out how to do it a little bit better. Okay. Let's convert our data. Rather than having the price of the stocks at every day, let's convert our data to how much it went up and how much it went down every day. Okay? So instead of it doing like this, first day it was 10, then it was 12, then it was 7, then it was 10. Rather than doing that, let's do the following. Let's change this into an array with a 2. I went up 2. Then I went minus 5. Then I went up 3. Dot, dot, dot. This will go on, this will go on. So again, rather than looking at the prices, look at the profits and the losses. Okay, great. Now, what do you want? You want to hold on to the stock long enough so that you make the most money. Okay. What that translates in terms of the arrays of profits and losses, the arrays of positive and negative numbers, is this is going to be a sub-array. In other words, you're going to have a giant array where each one of these things are going to have some positives and some negatives. Okay? I'm sorry, some of the numbers are positive. And what you want is a part of that array such that connected part of that array such that if you add up all the numbers in here, it's going to be the most positive, which means that you have as many making day monies, we have more making days monies, and the money you're making is more than any place else. Okay? Hence the phrase maximal subarray problem. Let's rephrase it. You're given an array of numbers, and you want to find a subarray, an array, a one-dimensional. You want to find a part of that array, such that when you add up all the numbers inside that array, it's going to be the highest possible number. Okay? Now this will solve the problem, and we'll see how to do it. Okay. And just keep in mind, if all your numbers are positive, what should you do? Okay, what should you do? You should buy at the beginning of the array and sell at the end of the array. In other words, what does that correspond to? If all your numbers are positive, that corresponds to the stock just going straight up, and all these numbers are positive, you take the whole array. Okay? If all the numbers are negative, what does that correspond to? That corresponds to your stock just going down and down and down. Don't buy anything. You won't lose anything. Your maximal subarray will be the empty subarray. You don't want to buy anything. Okay? And if you have to buy something, you buy you go through the array and search for the smallest number. That way you'll lose just the smallest amount that day. Okay? Okay, great. But sometimes you're going to have to buy and then sell. Let's watch this. Okay? Let's make this an 8. Okay? Look, you might want to buy it here. Okay? And just buy it for day 2. Or this change. Okay? That will be very nice. You'll only make $2. Okay? But look what happens. If you buy it here and take this, okay, I'm sorry, if you buy it here and sell it here, that's bad, because then you lost $3. Okay? So what you want to do, what the best possible solution for this case would be, even if you have negative numbers here, is this whole thing. Okay? If you buy it here and sell it here, look what you're going to make. Okay? You're going to make 2, you're going to make minus 3, plus 8 is, you're going to make $5 altogether. Okay? 2 plus 8 is 10, minus 5 is $5. Okay? But don't take this one and don't take this one. Okay, great. So, let me show you how we're going to do this recursively. We're going to solve the maximal subarray problem recursively, and it's going to be much better. And I'll show you why it's going to be much better in a second. Okay, here's what you do. You're given a giant array, and you're searching for the maximal subarray. Well, like I said, you can go through it kind of like a brute force search, but here's another thing you could do. Split the array into 2. Okay? Now, find the maximal. Now, where is the maximal subarray? Okay? Well, there's 3 possibilities. One is the maximal subarray could be in the first part. Okay? It could be somewhere along here. And again, think of this. This could be 500 elements here. So, it could be somewhere here. So, search for it and find it. Let's say this is the maximal subarray from this part. You could also have the maximal subarray could be this part. Okay? And let's say this is the maximal subarray. Okay? But there's a third possibility too. And I want to point out this third possibility. We're going to spend the most time with this third possibility. The third possibility is that the maximal subarray crosses this middle boundary. Okay? In other words, in order to get the most money, you have to do this and this. Okay. So the way, again, your maximal subarray could be either this red one, or this red one, or this green one. It could be on this side or that side. It's like when I'm looking for, okay. Okay, so you have to check all 3 of these possibilities. Okay, so the easy part is, I'm given an array, I want to find the maximal subarray. The easy part is, take this half, and send it into, recursively send it into the program that you're writing. Okay, so that's a recursive algorithm. Then, recursively send it into this. Send this part into the algorithm, and find the maximal subarray of this. And then, we have to worry about the green. What about that? Okay, so I'd like to show you how that works. Okay, the green. And we're going to come back to the whole algorithm in a second, but we need some room, and we have to show you how the green part works. Okay, so imagine, we'll do the algorithm also, but imagine for a second that the numbers you're given, sorry, I don't want to the numbers you're given are, let's do a real live example with real numbers. Minus 5, 28, minus 3, minus 7, 2, 4, minus 6, 5, 2, minus 13, minus 1, 12. Okay? And the boundary condition, not the boundary, the splitting is here. Okay, so I'm interested in this middle green thing, how much to the left I have to go and how much to the right I have to go. Okay, and so what we're going to do is we're going to try it. Okay, so let's try it. Let's see how much, first let's see how much to the left I have to go. Okay, this might take a few times, so you might want to watch this over again. Okay, okay, ready? If I take this 4 is a positive number. I'll make $4. That's good, I like making $4. If I take this, that would be great. I'll make $6. Okay, great. So far, if I go this, I'll make $6. Now, if I take this, I'll make how much? This will be 6 plus minus 7 is minus 1. So if I take this, I make minus $1. Now you might say, okay, stop. Just take 2 and 4. The algorithm doesn't do that. You have to go till the end. You have to go all the way to the end to make sure that you can make more money. Okay? So again, 4 plus 2 is 6. Minus 7 is minus 1. Minus 3 is what? Minus 1 plus minus 3 is minus 4. Plus 28. Okay, so anyways, I'm obviously not taking minus 4. I mean, that's not going to be helpful. So right now, my best bet is just to do this. Okay, but I keep on searching for what, maybe I could have a better bet. Okay, so right now it's 6. Okay, if I go here, it's minus 1, no good. If I go here, it's minus 4, no good. But if I go here, look how much money I would make. Minus 4 plus 28 is 24. Buzz, 24 is better than 6. 24 is better than 6. So I take this. Okay? So now I'm all the way up to here. Okay? Beforehand I was just up to here and I was just exploring. Now we go on. So I'm up to 24. If I take this, how much do I get? 24 minus 5 is 19. Buzz. Not interested. Okay, I'm at the end. Okay. I said stop. So that means I take this. Okay, so if I do all this, I'm going to make $24. Great. Now I have to deal with the right-hand side. How much should I take here? Okay, I'm going to take the minus 6 because I want to see how much to do. Okay, minus 6. Okay, so I'm going to take the minus 6 because that's better than negative infinity. You'll understand that in a second. Okay, then I take the 5. Definitely take the 5 because now my gains by going this way is only negative 1. Negative 1 is better than negative 6, so I better do that. Okay, next, I now have a gain on this side of negative 1. Should I take the 2? Absolutely. Okay, so I do that. Okay, great. So now, let's see, this is minus 6 plus 5 is minus 1, plus 2 is minus 1, plus 2 is plus 1. Should I take this? I'm up to plus 1. Should I take the minus 13? It will be negative 12. Not really. I should. Okay, I won't, so I'll just stick to this. Okay, now go on. What happens if I take this? It'll be negative 12, negative 13. Okay, still not good. Okay, but maybe I should take this. Negative 13 plus 12 is negative 1. Now here we had plus 1. Okay, it doesn't pay to do it. Let's go through this again. Okay, I should take the negative 6, yes, because that's better than negative infinity. Okay, I have to take something on this side. It has to take something on this side. Otherwise, if I just close this off, my solution would already be found from there, from the first example. Okay, so minus 6 plus 5 is minus 1. Minus 1. Here with this is plus 1. So right now my winnings are plus 1. Should I take the minus 13? No, because then I would have negative 12. Negative 13. Negative 13 plus 12 is negative 1. Now, should I take this? Should I get this big 12? No, because right now I'm making plus $1. If I took all of this, I'd be making minus $1. So we stop here. And we get it. Okay? Now, this whole thing is our, this whole thing is our middle thing that crosses the boundary. How much money did we make altogether? This is 24, and this is 1. I make $25 here. Okay? What I'd like to do is go through the algorithm that actually does this. Okay? And we do it with a black pen because it's an algorithm. Okay. Let me erase. Let me write it down. Okay. So we just went through the algorithm that finds the maximum subarray that crosses this middle boundary. And what you have to do is you have to go to the left and you have to go to the right. Okay. So. Okay. I just want to go. The algorithm is called find max crossing. Find the maximum that crosses, as opposed to find the maximum that's on the left, and in fact the maximum on the right. Okay, so let me just go through. This is one part of it. You'll see there's a whole other part also. So left sum starts as negative infinity. That means we're going to take the first example. Sum is equal to 0. That means when we start here, we count to 0. For I is equal to mid. This is mid. And this is down here. This is low. Obviously, this is high. Okay, so the midpoint, the high point, the low point. Okay, for I is equal to mid down to low. Sum is equal to sum plus a of I. So we're going to take that. If sum is more than left sum, okay, so the first one obviously is going to take because anything is more than negative infinity, and so we can do left sum is equal to sum. We're going to take that. Maxed left is equal to I. Okay, then we keep on going, keep on going. You go all the way to the end, and each time you add the number that you're taking, you compare it to what you had before, and you do it over and over and over. This should be a capital L. Okay. Anyways, you can see the algorithm on your own. It's on page 71. Okay, and as I said, this is only one part because when you finish this, then you have to go this way. And so you have the exact same algorithm, but every time you see the words left, you change it for the word right. Okay? Let's just go through again how this algorithm works. So this find max crossing does this, and so we have to go through this whole thing and see how it works all together. Okay, here's your entire, I forgot what numbers were here. Minus 13, minus 1, and 12. Okay, so you have the entire array. Okay, and in order to solve this array, you go through 3 steps. 1, find the maximum on this side, and you can already see what the maximum on this side will be. Just that. Take the 28. Next, find the maximum on this side, and you can see what the maximum on this side will be. Okay, just this. Maybe you should include 5 and 12. No, 5 and 12 won't do it. Okay, great. There's a small one, but obviously it doesn't have to do it. Then find the maximum of this, crossing the array. And you'll see how to do that. So you take this part, and we counted already that that's 24. Okay, and now when you want to find the maximum of 3 things, what do? You check them 2 at a time. Anyways, so what's bigger? 28, 12, or the green 24? And the answer is 28, 12, or 24. What's the biggest? 28. So we do that. Okay, but we're not really, okay, but, so this was a nice little algorithm. Okay, the question is, how much work was done? Okay, that's the question we always ask. And the answer is as follows. Look, depends on how many elements are in your array. But if you have n elements in the array, look what you have to do. Okay, you have to divide the array, do the left side, t of n over 2, do the right side, t of n over 2, and then you have to do the middle. You have to do the middle. Now let's see how much work is done in the middle. Notice what we're doing. You start here and you go down to low. Each time calculating. You're doing one comparison each time calculating, seeing, did I get better, did I get better, did I get better, all the way down to here. Then you do the other side and you go from mid to high. Go through. The point is, I do one comparison for every element to see if I should include it into this green box. Okay? And so I have to go through the entire array, and so that's that. Let's shorten this a little bit. This becomes 2t of n over 2 plus n. Okay? We saw that before. When did we see that before? We saw it before with merge sort. Let's remember how that worked. I want to sort things using merge sort. I split the array into 2, chop it in half, do the left side, do the right side, and then merge them together. How many operations is merging them together? Answer n. So that's n over 2, left side, right side, merge them together. Okay? And this has the same running speed. This is n log n. Okay, we're going to see that we can actually do this problem a little bit quicker. Actually, we're not going to see it. It's a dynamical programming algorithm, but that is very nice. Okay, great. Okay, so that's a nice example of using recursion and the recurrence formula that you get out of it. Good. Next, section 4.2, which is Strassen's algorithm for matrix multiplication. Okay? So let's go through this. Oops, sorry. Let's go through this. On the first day of class, we did matrix multiplication. And we said, if you have a matrix A and you have a matrix B, you can multiply them out and you get a matrix C. Assuming this is an n by n matrix and this is an n by n matrix, you get out an n by n matrix. And we saw the way of doing it. Okay? You do it, you take this column, you take this row, and you get this box. Okay, we saw how to do it. Okay, now Strassen was a very smart man, and he said, you know what? Can't I do this recursively? Okay, can't I do this recursively? Okay, so let's see what he did. What is recursion all about? Recursion is all about chopping a problem into little parts. So, take this n by n matrix and chop it into 4 parts. Take this n by n matrix and chop it into 4 parts. Okay, and what you're going to get out is a matrix with 4 parts. These are capital letters. They're similar to these capital letters. Okay, great. Now, let's look at this. How big are each one of these matrices? Well, if the matrix is n wide and n long, then this, each one of these matrices is going to be n over 2 by n over 2. N over 2 by n over 2. Okay? Same thing here, same thing here, same thing here, same thing here, 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 here. Each one of these is an n over 2 by n over 2 matrix. Great. Okay? Now, how does it help us? Well, let's say I wanted to multiply these matrices. Here's the way I do it. You ready? It works with multiplication. Okay? In order to get this element here, some element that's in here, I need to get some column over here and some row over here. Okay? Plus a row here, plus a column here. Okay? So it's going to come together as follows. Okay? It's going to come together as follows. Okay? Basically, instead of doing it column and rows, I'm going to do it, each one of these are blocks. So I'm going to do it block by block. And you'll see how it goes. You ready? Let's figure out what C11 is. C11 is going to equal to, take this block, lift it up, go across. It's going to be A11 times B11 plus, we also have to do this times this. Remember, it's this times this. So watch my thumb. This times this. So it's A12 times B21. Okay? What about this block? Okay? It's going to be this block times this block. So it's going to be C12 is going to equal to A11 B12 plus yeah, okay. Plus, that's this times this. A12 times B22. Okay, good. Next, C21, that's down here. That's going to be this times this. So it's going to be A21 times B11, that's this times that, that's this times this, now this times this, plus A22 times B21. Okay? And finally we got to do this one, this last one. This last one is C22. Okay? So it's the bottom, the bottom right block, and so it's going to consist of the right column, the bottom block. Okay, and so it goes as follows. That's a B, by the way. Okay, so that's going to be A21 times B12 plus A22 times B22. Okay. Okay. Now, each one of these multiplications is an n over 2 by an n over 2, plus an n over 2 by an n over 2, n over 2 by an n over 2 by n over 2, n over 2 times an n over 2 by n over 2, etc., etc. Okay. So, if I was to write this line as a part of my program, it would be something like this. Matrix mult, okay, A11, comma, B12, that's this line. Okay, okay, matrix multiplication takes two things, and then add matrix mult of, let's see, A12, comma, B22. Okay, so that's the way you would do this line in the algorithm. Okay, great. Question: how much work was done? Okay, so I'm going to go over here. I need all the space I can. How much work was done? Okay, so let me put it another way. I have two n by n matrices. I want to multiply out two n by n matrices. So I chop up the problem into these small problems, small multiplications. Okay? I chop up the matrices into small n over 2, half the size. So it's going to be something about t of n over 2. Okay. Okay. Now, let's count how many multiplications you're going to have to do. Ready? This is important, so let's do it with a different color. Ready? How many little multiplications am I going to have to do? I'm going to have to multiply half matrices by half matrices, but how many? Ready? 1, 2, 3, 4, 5, 6, 7, 8. Okay? So I have to do 8. So I'm going to write this as equals. In order to multiply an n by n matrices, do 8 n over 2 matrices plus. Okay, now I do a lot of additions here. A lot of additions. 1, 2, 3, 4. Okay? Anyways, it turns out these additions are additions of matrices. Okay? And so it comes out n squared. Okay? Theta of n squared. Okay, great. That's very nice. Question. How much is this? Okay, now we didn't really work this out. By the end of this chapter, you'll know how much work that is. You can do it yourself. You'll be able to do it yourself. We'll do a Master Theorem in the last section, but you'll figure it out. But I'll give you the answer right now. You ready? The answer to this is t of n equals, ready? Hold on, n to the third. N to the third. Well, that didn't help you a lot. That didn't help you a lot at all, because the first day of class we did an algorithm without this fancy recursion, and it was also n to the third. So how did that help you? Answer, it didn't help you. Okay? So let's just review what we just did. We tried to use recursion to figure out matrix multiplication. We did it, but after calculating how much work is done, we didn't help us. Okay? Great. Okay. That doesn't help us. But Mr. Strassen was a very smart man. Okay? And he said, you know what? Instead of calculating these 4 half matrices using 8 things, maybe I can do it a different way. Okay? And so now we come to Strassen's algorithm. That was just regular matrix multiplication, but using recursion. But now Strassen said, you know what? Maybe I can do better. Okay, so let me show you what he did. It's a trick he had. Doesn't matter what the trick is, really. I'm going to be a little bit quickly about it. You're not responsible. You're not responsible to understand the trick. Nobody understands the trick. It just works. Okay, watch this. What he did was he made 7 matrices. P1, P2, P3, P4, P5, P6, and P7. Okay, let me show you what he did with these 7 matrices. Well, let me show you how he defined these 7 matrices. He said this is equal to A11 times B12. Okay, minus A11 times B22. Okay, doesn't matter. Don't try to think about what it is. Notice minus. Okay, and P2 he said was A11 times B22 plus A12 times B22. Okay, great. P3 was something like that. P4 was something like that. I'm not interested. You can look it up in the book. The trick is not an understandable trick. Okay? But let me just tell you what P7 is. P7 is A11 times B11 plus A11 times B12 minus A21 times B11 minus A21 times B12. Okay? So, he got these. Now, I just have to warn you not all of these are the same. Not all of these are different. Notice this is the same as this. Okay? And that's about all I see now. Okay, but there's a few more in there also. Okay? Now, once he has these, he's not interested in these P algorithm, but what he's interested in is the following. Ready? He's interested in what's the output of the matrices. Okay? Okay? And so he has the following. C11 is equal to P5 plus P4 minus P2 plus P6. C12 is equal to P1 plus P2. C21 is equal to P3 plus P4, which is equal to P5 plus P1 minus P3 minus P7. Doesn't matter. The point is as follows. Notice only additions here. Lots of multiplications and additions. Okay, point is, he's going to have a lot of these different things. If you actually sit down, write this out. Write down what P5 is. Write down what P4 is. Minus P2 plus P6. If you actually add it up, you'll get the same thing that we got before. Okay? Keep on doing it. For all of them, you'll see you get the same thing. It's a trick, but here's the kicker of the trick. You ready? Now we're about to figure out how much work Mr. Strassen's algorithm was. We're not interested in this algorithm because this didn't help us, but how much work Mr. Strassen's algorithm was. Well, notice you only have to do this multiplication once because it's even though it shows up more than once. Okay? So you only have to do it once. Okay, so it turns out if you go through all these things and you count how many multiplications of half matrices you have, you'll have the following. T of n, this is Strassen's algorithm, Strassen. Okay, T of n is equal to, now each one of these is an n over 2 by n over 2 matrix. So it's going to be a T of n over 2. Okay, and how many are you going to have? Okay, and also you're going to have a lot of matrix addition. A lot of matrix addition. Subtraction, subtraction, subtraction. Okay, so it's going to be n squared. A lot of them. Okay, but how much matrix multiplication? The key point is matrix multiplication is harder than matrix addition and subtraction. Okay, how many? Ready? Strassen calculated. Again, you can go through these P's. You can look on the page and see how many different you're going to need. And answer, you're going to need 7. Wow! He got it down from 8 to 7. He got it down from 8 to 7. That was his trick. By doing all this crazy manipulation, he was able to get it down to 7. Okay, now comes a great question. How much work does that take? Well, again, you'll know this by the end of this chapter, but it turns out that this is equal to T of n. If you find a function, you find the closed form of the function, it's going to be equal to n, hold on, to the log base 2 of 7. Okay? Which equals to n to the 2.807. Okay? Great. Let me just show you what happened. Strassen's algorithm was n to the 3rd. This algorithm is 2.807. That's a lot. I mean, that's not a lot. It's not a lot, but it's enough to make a difference. Okay? Nowadays, people do algorithms, a lot of algorithms, that help you a lot. So they can get this down to something like n to the 2.6. Nobody knows how much they can get it, but it makes a difference. Okay? If you don't believe me, one of the things I said was, it's very easy to make a matrix multiplication algorithm. Take a matrix multiplication algorithm, okay, and take a 500 by 500 matrix, multiply it by itself 500 times, and see what you get. I told you that's a big difference. That's a big thing if you have n to the third algorithm. Okay, it's a lot better if you have n to 2.6. So Strassen's algorithm works. It's the beginning of a whole field of mathematics to try to make these things much better. And you're welcome to look into it. But the reason why we did this was a divide and conquer algorithm. You had an n by n matrix, you divide and you conquer. Just want to go through one thing from the previous section that I skipped over a little bit too fast. Okay, where you saw that real difference. Let me just explain to you one thing. We're going back to that previous thing. We were doing maximum subarray. Max subarray. Okay, I want to concentrate on that for a second, because one of the things we said was you could do it in n squared time. Okay, and then I said, oh, but if you do it with this recursion, okay, where you split the thing in half, then you get it into n log of n. Okay, now I want to try something. Let's say you have 4 million numbers in your array. Okay, you have 4 million, n is equal to 4 million. N is equal to 4 million. Well, n squared will then be a million times million is trillion, so this will be 16 trillion. Okay? As opposed to that, n log n, you might say, oh look, n log n, n is more than n, so it's not linear, it's not whatever, it's more than linear. Okay? 60, so this is going to be 4 million times log of n. Maybe we didn't do it here, but we did that. Log of 4 million is 22. So this is equal to 4 times 22, 88 million. Okay. Question: what's better, 16 trillion or 88 million? Okay. Now imagine you can do a million operations in a second. So this becomes 88 seconds. Okay, how about that? Okay, how about that? I don't have my cell phone, so I can't calculate what 88 trillion, but 88 trillion is hundreds of millions of hours. So, well, it's a lot of hours. So it's better to do this than that. Okay, so let's recap. We went through 2 examples of real recursion algorithms, and we calculated how much work is done. Hold on one second. How many hours is 88 trillion? Oh, hold on. Okay, I'm sorry. It's not 88 trillion. It's 88 trillion operations, but you can do a million operations in a second. So you get that down to billion. So this is 16 million seconds. Okay, so now we calculated how much. How many hours is 16 million seconds?
16 million seconds is 4,444.444 hours.
How many days is 16 million seconds?
16 million seconds is equal to 185.185 days.
Okay, so what's better, 88 seconds or 185 days? So you might say, oh, n squared, n log n, what's the big difference? It's a big difference. Okay, it's a big difference. Okay, so next part, and the next part of the chapter is we go through how did we get rid of these recurrence formulas and just get functions. That's what we're going to do next. Section 4.4 and 4.5. Okay. This is section 4.4. It's called the recursion tree method for solving recurrences. Okay, and the idea is as follows. Okay, our goal is to take a recurrence formula and make it into a real life function. We like functions. We don't like recurrence formulas. Okay, how do you do it? Well, the thing is that you can look at recursion as a type of programming, and what it does is it makes a tree. Okay, and so for example, let's talk about that merge sort. Okay, we sort it as follows: T of n is equal to 2 times T of n over 2 plus n. Okay, the way to think of this is as follows. You have some T of n. Question: how can I write this in another way? Well, what you do is basically you split this up into 2 parts. Okay, so it becomes a tree. Okay, the left side and the right side. Okay, merge sort. How do you do merge sort? You sort the left side, then you sort the right side, then you merge them together. You split them up. Okay, but you can't just split them up. It takes certain operations to do that, so you do it as n. Okay, that's great. Okay, now, but what does this become? Well, we make another tree, and it says as follows. Well, you have the n here from before, and this is going to become n over 2, and this is going to become n over 2, and this is going to split into 2 things. Each one is going to be split into 2 things, and that's going to be n over 4. T of n over 4. T of n over 4. Okay? Okay, and so you build this tree. We're actually going to build not a tree, but a sequence of trees all the time, building these sequence of trees. And then what we do is we want to know how much work is done. Well, how much work is done is how many of these numbers on the tree. So we do that. Okay, we calculate that. Okay, good. Now, we're going to see a lot of examples of this. So I'm just trying to motivate you. Okay. The book goes a little bit quickly. Okay, it starts off a little bit quickly. It starts off you can understand things more than quickly. So what I do is I put in a little bit of a few filler steps. Okay, and so we're going to talk about 3 examples, A, B, and C. Okay, of recurrence formulas, and we're going to use trees to calculate what they are. Okay, and once we do that, we're going to get the feel of it, and we're going to understand what's going on, and then we'll do it a little. Then we'll do the examples from the homeworks and stuff like that. So let's do that. Okay? Okay, so let's start with A. Okay? A says as follows. It's a recurrence formula that says A of n is equal to 3 plus A of n minus 1. Okay? But I need a base case also, so we say the base case is A of 1 is equal to 2. So again, this is a recurrence formula because what A of n is equal to depends on previous values. Let's just do a warm-up exercise. A of 4 is equal to 3 plus A of 3. Okay, which is equal to 3 plus A, what's A of 3? Plug in 3 here, you get 3 plus A of 2, which is equal to 3 plus 3 plus 3 plus A of 1. What's A of 1? So this is equal to 3 plus 3 plus 3 plus 2. A of 1 is equal to 2. Okay? So that's your warm-up exercise, and that's equal to some number, 11 or something like that. But that's not important. What's important is how it worked, and the way it works is every time you go down 1, you add a 3. So how many times do you go down from 4 to 1? And the answer is 3. So it's another way of saying this is 3 times 3 plus 2. Okay? Okay, but now that we understand it, we can figure out what A of n is. What's A of n? Okay, A of n is every time you go down till 1, you're going to multiply by 3. So it's basically 3 times n minus 1. And don't forget the last thing. The last thing is plus 2. Okay? And now, very simply, now I can figure out what A15 is, because now this is a function. This is not a recurrence formula. That's a recurrence formula. Now we have a function, and I plug in A of 15, and I get 3 times, or A of 16, 3 times 15 plus 2. 3 times 15 is 45, plus 2 is 47. So it's very easy to calculate. So we like functions, and that's why we do it. Okay, but what I really want to do is not just solve it, but I want to show you how it's solved using trees. So let's do it with trees. Okay. And again, what we do is we make a sequence of trees. We start off like this. A of n. Okay? And I'm doing it like this because that's the way the book does it, and I want you to follow along the book, and I want you to see it in the book. Okay? So A of n is really, you put the 3 there, and then it becomes, it has one child, A of n minus 1. Okay? Great. Now, what's the A of n minus 1? So again, you're building these trees. So this is a 3, and A of n minus 1 is equal to 3 plus A of n minus 2. Okay? Okay, and this becomes 3, 3, 3, A of n minus 3. Okay? And this goes on. Okay? Good. At the end, what do you have? Dot, dot, dot. Okay? This is going to be A of 1. Okay? And so this is going to be 3, 3, 3, 3, dot, dot, dot. Okay? There's going to be a 3 over here. And then you're going to have A of 1. A of 1 is another way of saying 2. Okay, great. Question. How tall is this tree? This is a question we're going to ask over and over. How tall is this tree? Anyways, from here till here is n minus 1. Okay? And the whole tree, you start from n, A of n, down to 0. Okay? And so you get that. Okay, so the whole tree, the height of the whole tree is n, but where until there is n minus 1. So basically, now what you have to do is you have to add these up. Well, what's on your tree? Okay, answer, okay, it's 3 times n minus 1. That's how many layers you have that have 3, okay, plus 2. Well, that's exactly what we had before. Okay, but now we see it as a tree. So basically what we're going to do here is we're going to build a sequence of trees, and then we're going to add up what's on the tree layer by layer. Obviously things are getting more and more complicated, but this is a very simple thing. And then this is the amount of stuff that's left on the tree. Okay, great. So that's the A example. Let's do a little bit more complicated example. And the more complicated example is B of n. Okay? And B of n is going to equal to, instead of doing addition, we're going to deal with multiplication now. 3 times B of n minus 1 plus 2. I'm sorry. Just 3 times B of n. Okay? But now the boundary case is B of 1 is equal to 2. Okay. Let's work out this. So let's do a warm-up exercise. B of 4 is equal to 3 times B of 3, which is equal to 3 times 3 times B of 2, which is equal to 3 times 3 times 3 times B of 1. Okay, and B of 1 is 2. And so this is equal to 3 times 3 times 3 times 2. Okay, good. That was a good warm-up exercise, and this is equal to something. I'm not interested. This is equal to something, but we use this now to figure out what B of n is, because what did we see happens here? Every time we go down 1, we multiply by 3. Okay, so if you're going to do a B of n, every time you go down by 1, you're going to multiply by 3. How many times do you go down from n to 1? And the answer is n minus 1. And each time you're going to multiply by 3. So you're going to get 3 times 3 times 3 times 3 times 3. Okay, and then the last thing you're going to do is multiply by 2. How many of these guys do you have? N minus 1. Okay, so a neater way of writing this is 3 to the n minus 1 times 2. Okay. And of course now we can figure out what B of 15 is. Okay, I plug it in. It's going to be 3 to the 14, that's some humongous number, times 2. Okay, but again, we're not interested in doing it by calculating it, we're interested in doing it with a tree. Okay, so let's do it with a tree. And the tree is as follows. Again, it's a sequence of trees. B of n is like that. Okay, and then what we do is B of n has 3 children. B of n minus 1, B of n minus 1, B of n minus 1. Okay, okay, now I can go on and do this again. Okay, but the truth is, I don't change these things because we're not really adding numbers here. There's nothing numbers here. But so we can do it like this on the same tree. So I don't really need a sequence of trees. I can do it like this. This is B of n minus 2, B of n minus 2, B of n minus 2, etc., etc. Okay, we're going to have 9 copies of B of n minus 2. Okay, and then this goes on. He's going to have 3 children, B of n minus 3, B of n minus 3. Okay, there's going to be 27 copies of here. If there's 3 copies here, 9 copies here, 27 copies here. Okay, great. Eventually, what are you going to have? You're going to go down to 1. B of 1, lots and lots and lots of copies of B of 1, and B of 1 is equal to 2. Okay, 2. Okay, great. Now, we do what we always do. We add up how many numbers are on the tree. Well, there are no numbers on the tree until the bottom layer. Okay, so now we ask the following question. How many numbers are in the bottom layer? Okay, in order to solve that, we have to solve how big is the tree. Okay, so let's go through it. First of all, how tall is the tree? Okay, and the answer is the length of the height of the tree is really length n. Okay, you go all the way, well, maybe n minus 1. Sorry, n minus 1, because you go till B of 1. So from n to 1 is n minus 1. Okay, and there's no numbers here. You're not adding up any numbers here. But how many numbers are down here? And the answer is, well, let's go through it. There are 3 to the 0 here. There's 3 to the 1 here. There's 3 to the 2 here. There's 3 to the 3 here. There's 3 to the n minus 1 here. Okay, that's the bottom layer, and that's the only layer that has numbers. And how much numbers do you have? And the answer is each one of these leaves on the bottom of your Christmas tree has 2 things. Okay, and that's your final sum. Okay, you don't have to sum up all these guys because there's nothing there. Okay, so again, for A we had a very thin tree. For B we have a wide tree. Okay, but there's only things on the bottom. Okay, now we have to make it a little bit more complicated and have things on the tree here also. Okay, so that's the B example. let's do the C example. Okay. A just had addition. B had multiplication. C is going to have addition and multiplication. Okay, so let's do it. C of n is equal to 3 times C of n minus 1 plus 2. Okay, and the base case is C of 1, which is equal to 2. Okay, now let's do a warm-up exercise. C of 5 is going to equal to 3 times C of 4 plus 2, okay, which is equal to 3 times, what's C of 4? 3 times C of 3 plus 2 plus 2. Don't forget that plus 2. Okay, let's combine terms before we do anything. This becomes 3 squared plus 3 to the 1 times 2 plus 2. Oh, shoot, hold on. Sorry. 3 squared times C of 3 plus 3 to the 1 times 2 plus 2. Okay, great. Now let's figure out what this is. This is equal to 3 squared times 3 times C of 2 plus 2. Okay, that's C of 3, that's right there is C of 3, plus 3 to the 1 times 2 plus 2. Okay, I'm going to write, instead of writing plus 2, I'm going to write 3 to the 0 times 2. It's the same thing. Okay, but the point is we have a sequence here. 0, 1, this is going to be, okay, let's multiply it out. This becomes 3 to the 3rd times C 1 oh, sorry, C to the 2, 3, let's multiply it out. 3 squared times 3 is 3 to the 3rd times C to the 2 plus 3 squared times 2 plus 3 to the 1 times 2 plus 3 to the 0 times 2. Okay, and what's C squared? So this is equal to 3 to the 3rd times 3 times C to the 1 plus 2, okay, plus 3 squared times 2 plus 3 1 times 2 plus 3 0 times 2. Okay, and so this all ends up to be 3 to the 4th times, what's C2? C1. C1 is equal to 2 times 2 plus 3 to the 3rd times 2, 3 to the 3rd times 2 plus 3 to the 2nd times 2 plus 3 to the 1 times 2 plus 3 to the 0 times 2. Okay? Now we can write this a lot nicer as this is equal to 3 to the I equals, we start at 0 till 4, 0 to 4 times 2. Okay, let's do this. This goes to the front, so this equals to 2 times the sum of I equals 0 to 4 of 3 to the I. Okay, we know how to do this. This is the geometric sum, so let's do this. This is equal to 2, don't forget the 2, okay? And let's remember what the geometric sum is. You can look it up, whatever. We did it in class, we did it here. Okay, so this becomes 3 to the 4 plus 1 minus 1, and then x is 3 here, so this becomes 3 minus 1, and you get that. Okay? Okay, 3 minus 1 is 2. This 2 cancels out with that 2, and so you're left with 3 to the 4 plus 1. That's 3 to the 5. Let's write it up. 3 to the 5, sorry. 3 to the 5 minus 1. Okay, great. Now, that's if we plug in 5. Yeah. let's say we plug in n, C of n. Notice what happens. You're going to multiply these two all the time, okay? C to the n, you're going to multiply the two all the time, okay? And each time you're going to do that. Okay, so that's going to be the sum of I equal 0 till n minus 1, just like before. Whoops. Right, n minus 1. We plugged in C of 5, we got till n minus 1, okay, of 3 to the I times 2. Again, the 2 goes to the front, okay, and you're left with same thing, 2 times, okay, let's write it out, I equals 0 till n minus 1 of 3 to the I, okay, this is equal to 2 times geometric formula, so this becomes 3 to the n minus 1 plus 1, so that's 3 to the n, okay, minus 1, divided by 3 minus 1, that's the geometric series. This cancels out with this, and you're left with 3 to the n minus 1. Okay, that's very nice. Okay, great. But again, this is doing it by adding. I like to do it by the trees, but it works out very nice. And again, here you see both the multiplication and the addition working together. Okay, here the trees are going to be a little bit more complicated, but that's fine. Okay, so basically it's C of n. That's a dot. Okay, okay, we're going to change this dot into what? Okay, let's remember the formula here. Let's remember the formula. C of n is equal to 3 times C of n minus 1 plus 2. Okay, so we're going to change this formula. The C of n becomes, you put the 2 up, because that's how much work you have to do, and then you have 3 children. Each child is C of n minus 1, C of n minus 1, C of n minus 1. Now we make another tree where we change this. I can erase this, but it's harder to see. I can erase this and put down the 2's, but I want you to see us forming the tree. Okay, this becomes 2, 2, 2. Each one of these have 3 children, okay, which each child is n minus 2. And there's going to be 9 children with the words n minus 2. Okay. Next, build another tree. But now I'm getting bored, and so we're going to do it a little bit quickly. It's going to be 2, 2, 2. No, you know what? We're going to build the tree over here because we need the space to calculate the tree. Okay. Okay. So you do a sequence of trees. You get a feel for what it's going to be, and then we do it. Okay, so this is going to be 2. It's going to have 3 children. Each one of them is going to be a 2. And each one of those is going to have 3 children. Oops. And this is going to be 2, 2, 2, 2, 2, 2, 2, 2, 2. 9 children. Each one of these has 3 children. Okay. Ba 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 ba. 2 bunch of 2's. Okay. Okay, great. Now let's go through it. Now I have a giant Christmas tree. At every level there's 2's, and I have to add them up and see how much there are. Okay. Okay. The way you do it is layer by level by level. So this is 2. There's just 1 2 there. Okay. This is 2 plus 2 plus 2 is 6, but I don't want to write it as 6. I want to write it as 3 times 2. Okay. And this is 9. I want to write it as 3 squared times 2. And this is 27. I want to write it as 3 to the 3rd times 2. Just to keep up with the form, I want to write this as 3 to the 0 times 2. 3 to the 0 is 1. Okay, dot, 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 3 to the n minus 1 times 2. Let's see why it's n minus 1. This is level n. This was c of n. I go all the way down to c of 1. Okay, this n minus 1 things there. Great. Now I've mapped up each level how much there are. Let me just do the arbitrary in the middle case. This is 3 to the I times 2. Okay, and now I add them all up. Okay, and what do we get? I bring the 2 to the outside, and I get out I equals 0 till n minus 1 of 3 to the I. Okay, and we worked that out already. Okay, this is equal to, using the geometric series, this is equal to 3 to the n to m minus 1. Okay, so now we finished the 3 examples. We had thin examples, wide examples, and wide examples with numbers on it. But the ideas remain the same. The idea is as follows. We formulate the tree, we add up all the elements on the tree, we sum up all the elements of each level, and we get out an answer. Okay? Okay. Let me just tell you, the book does some examples. We don't do the book's examples. We're going to do 3 examples of trees now, real live examples of trees. The book does a few examples, 3 or 4, and then I gave you a homework sheet, and I gave you the answers to the homework sheet. So you see 4 or 5 more of those trees. Okay, so you're going to see a lot. Okay, the first example I'd like to do is what we started with, namely that thing about merge sort and max subarray, namely 2 of t of n over 2 plus n. Okay, so I'd like to make this tree. Okay. Oh, you might. First of all, there's a little difference here. First of all, beforehand, the previous 3 examples, everything I did was n and then n minus 1. Now I'm doing n over 2. So that's a little bit more complicated. We'll have to see. It's interesting to see the height of the tree. Okay? The second difference, okay, is I don't care about boundary cases. Okay? And the reason is as follows. I just want to say, for small inputs, the boundary is 1 or 2. I don't care. Constant amount. Okay? But that's how much work is done. But I don't care about it, and the book doesn't care about it. Another thing we don't care about is floors and ceilings. We don't care about that. The book talks about it, but we're gonna leave that out. So this was the recurrence formula for merge sort and max subarray. Okay, let's start making trees. Start off with t of n. Okay, then you say, oh, t of n becomes n, and it has 2 children, namely t of n over 2 and t of n over 2. Again, I can erase this, but I want you to write in everything so you get to see it. Okay, I want you to see the way the tree is coming up. This is n over 2, this is n over 2, and each one has 2 children called n over 4, n over 4, n over 4, n over 4. Okay, dot, dot, dot. This becomes, okay, n over 2, n over 2. Okay, when you plug in n over 4 here, what do you get? You're going to plug in n over 4 here. You're going to get 2 children. He's going to have 2 children. N over 4 is going to have 2 children, and then it's going to put in n over 4 over here. So this is going to be an n over 4 here, and he's going to have 2 children called t of n over 8. Okay, and we're going to get that n over 4 dot dot n over 4 n over 4, and here's going to be n over 8, and there's going to be a lot of copies of n over 8, etc., etc. Okay, a lot of copies of n over 8. How many copies of n over 8? 1, 2, 4, 8 copies of that. Okay? Going down, Okay, this is going to go down. This is going to, he's going to have, let's just do it, n over 16, dot, 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 dot. Okay, and finally we're going to get t of 1 here. Okay, okay. Question, this is going to go down also, and you're going to have t of 1 over here. Question, how tall is this tree? Okay, now before, when we went from n to n minus 1, we said, look, oh, you have the tree is until you get down to 1. Here, you're going to go n until you get down to 1. Each time you're dividing by 2. Divide by 2, divide by 2. Question, how many times can you divide n by 2? And the answer is log of n. Okay? This is what we said about exponential. Exponential is multiplying by 2, and we're interested in dividing by 2. So, log of n. Answer. The height of this tree is log base 2 of n. Okay, great. Now let's go through what each tree has. This has n. This has 2 times n over 2. What do we call that? N. This has 4 copies. I don't want to write 4. I want to write 2 to the 2 copies of n over 4. I don't want to write 4. I want to write 2 to the n. 2 to the 2. Okay. How about this? This has 8 copies. This has 8 copies because there are 4 people here. Each one has 2 children, so there's 8 copies. I don't want to write 8. I want to write 2 to the 3 times n over 2 to the 3. Dot, dot, dot. In general, you're going to have 2 to the I copies, and each one is going to be n divided by 2 to the I. Okay, great. Now, we need some space. And so, I want to add up all these things. Dot, dot, dot. I want to add them all up. So let's add them all up. You ready? By the way, what is each one? Oh, what's this? I'm going to write this as 2 to the 0 divided by 2 to the 0. So basically, this becomes the sum of I equal 0 till log base 2 of n, okay, times 2 to the I times, I know I'm doing this silly because I know when you multiply each one of these is n, but I want to do it because we're going to see it in the next example. In the next example, we're always going to do it this way. So let's do it. This is n divided by 2 to the I. Okay, good. Now, cross this out, and so you get this is I equals 0 to I to log base 2 of n of what? Of n. This is the silliest thing in the world. Notice I doesn't show up here. In other words, you can think of this as 1 times n. This goes to the beginning, and so basically this becomes n times the sum of I equals 0 to log base 2 of n of 1. You add this up. How many times are you adding 1? Answer, log base 2 of n. So this becomes n times, this whole thing becomes log base 2 of n. N log n. I told you in the beginning, I told you the first day of class that this is about n log n. Now we can see why it's true. Okay, so basically, let's just go through it. This is nice pictures, and again, I did this because we're going to do this over and over again with other examples, but basically, each layer gives you size n, and how high is the tree? Log of n. So it's n times log of n. That's it. Okay, let's do a little bit more complicated of an example. Okay. Let's do a little bit more complicated example. Okay, I just want to say the book does, again, I want to hold your hand while you do the book. The book does t of n is equal to 3 times t of n over 4 plus n squared. Okay? Okay, great. So the book does that. You're going to read the book, but we're going to do this. T of n is equal to 4 times t of n over 2 plus n. Okay, so the difference really is, oh, he's doing n squared, he's doing that. That's fine. I'm just showing you that the book does, but basically we're going to do this. So let's do this one. Okay. It's similar to the previous one, but instead of doing 2 copies, usually he has 4 children. Okay, okay, and again we're ignoring ceilings and things, floors and ceilings. Okay, that's 1. Okay, then he has n children. Then he becomes n, and he has 4 children. Each one is n over 2. Okay, t of n over 2. Dot 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 t of n over 2. Okay. Then this becomes n over 2, n over 2, n over 2, n over 2, and he has 4 children also. Okay, and each one of them becomes n over 4. Dot, 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 t of n over 4. Okay, there's going to be 16 copies of that. Okay. Okay, good. Now, build another tree. Okay, I can erase, you can't erase, you have to write. Okay, and the next tree is going to have n over 4, n over 4, dot, 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 n over 4. Okay, and he's going to have n over 8. There's going to be 4 copies of this, n over 8, dot, 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 dot. Okay. There's going to be 4 copies of that, and you're going to have n over 8. Let's just do one more. This is going to be n over 16. Okay, and how many copies of that? Well, if there's 4 of these, there's going to be 16 of these, there's going to be 64 of these, etc., etc. Okay? N over 16. It's going to be a lot of these guys, just like there's a lot of these guys. Okay, great. Question. How high is this tree? Well, it's the same thing because you're dividing by 2. How many times can you divide by 2? Answer, log base 2 of n. Okay, so the height of the tree is log base 2 of n. Question. Let's add up things level by level. So this is n. That's good. This is what? I'm going to write it as 4 to the 1 times n over 2. Okay, I need space over here too. This is going to be 16, so I'm going to write this as 4 to the 2 times n over, I'm not going to write 4. Okay, I'm going to write it as 2 to the 2. Okay, you see that pattern going on here. How about this? This is going to be as many as these are times 4. So that's going to be 4 to the 3rd times n divided by 2 to the 3rd. Okay. In general, dot, 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 in general, you're going to have 4 to the I times n over 2 to the I. Dot, dot, dot. Okay. The bottom here is all going to be 1s. Okay. By the way, this should be 4 to the 0 divided by 2 to the 0. Okay. Okay, great. Now what we do is we add them all up. Okay, so let's all add them all up. The sum I equals 0 till the height of the tree. What's the height of the tree? Log base 2 of n. And each one is going to be, okay, let's fix this beforehand. What's 4 to the I divided by 2 to the I? Well, that's going to be 4 to the I divided by 2 to the I times n. Okay, this is going to equal to, what's 4 over 2? This is going to equal to 2 to the I, 4 cancels out with 2, times n. Okay, and so this becomes 2 to the I times n. The n can go to the front, so I'm going to put the n over here. Okay, let's finish it up over here. This is equal to, hey, we've seen this before. That's Mr. Geometric Series. So this becomes, this is equal to n times, we actually even did that example, well, not with that boundary, so this becomes 2 to the log of n plus 1 minus 1 divided by 2 minus 1, so we'll write that 2 minus 1. Okay, what's 2 minus 1? That's 1. Let's leave that alone. So this becomes n times, okay, 2 to the log of n plus 1, that's just multiplying by 2. The plus 1 is 2 to the 1. Okay, that takes care of that, times, what's 2 to the log of n? Log base 2. 2 to the log base 2 of n, that's n. Okay, okay, hold on. Don't forget the minus 1 here. Okay, and so this is equal to, this is equal to 2 times n, which is 2n squared, okay, minus n. So this is a member of theta of n squared. That's it, it's n squared. So if you change it, we did the previous example had a 2 over here, and we got n log n, and here we have a 4, we get n squared. So that's a nice example. Okay, good. Okay, one more example, and we get sick of trees. Okay. Okay. One more example. Now obviously this is going to be the most complicated one we're going to see. Okay, this is equal to 2. Each one has 2 children of t of n, 3n over 4, 3n divided by 4 plus n. Okay. I'd like to rewrite this, and you'll see why in 2 minutes. This is equal to 2 times t of, instead of writing this as 3n over 4, I'm going to write this as n divided by 4/3. Okay, the reciprocal of 4/3 is 3 of n, plus n. Okay, so let's start our trees. T of n, he's going to change into an n, and he has 2 children. One is n over 3n over 4, 3n over 4, t of 3n over 4. Okay, and this is going to change into n, 3n over 4, 3n over 4, and he's going to have 2 children, and he's going to have 3 children. And here's the hard part. So this is why I want to do this. This is very important. I plug in 3n over 4 into here. I get in 3 squared over, plug in n is equal to 3n over 4. So 3 times 3 is 3 squared. Divided by 4 is 4 squared n. Same thing here. T of 3 squared, sorry, the n goes over there, n divided by 4 squared n. 4 squared, dot, 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 dot. 2 more. Okay? Okay. Okay, let's do this just numbers. Dot, dot, dot. Okay? This is 3n over 4. This is 3n over 4. Each one has two children. 3 squared n over 4 squared. 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 Okay, this is going to be 3 to the third n over 4 to the third. Okay, and we're getting bored. Okay, in general, dot dot dot, we're going to have 3 to the I n over 4 to the I. Great. Okay, now let's calculate layer by layer. So this is going to be an n. This is going to be what? This is going to be 2 copies of 3 to the n divided by 4. This is going to be 4 copies. Oh, I'm not going to write 4. What am I going to write? I'm going to write 2 squared. So this is 2 to the 1 of 3 squared n. That's what you have. 4 copies. 1, 2, 3, 4 of 4. 4 squared. Okay, great. Okay. Dot, dot, dot. Let's do the next one. Here you're going to have 1, 2, 3, 4. Here you're going to have 8 copies. You're going to have 2 to the third copies of 3 to the third n divided by 4 to the third. Okay. In general, dot, 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 you're going to have 2 to the I copies of 3 to the I times n divided by 4 to the I. Okay. Boom, 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 boom. Now, okay, so far, just the same, okay? But, question, how high is this tree? How high is the tree? Okay, you're not splitting it by 2 every time. You're not splitting it by 4 every time. How much are you splitting it by? Okay, and that's why we wrote this. You're splitting it by 4/3 every time. Okay? You're dividing by 4/3, dividing by taking n, divided by 4/3, divided by 4/3, divided by 4/3, until what? Until you get to 1. Okay? How many times can you divide n by 4/3? Okay? And the answer is log of n base 4/3. Okay, good. So that's why I wrote it like that. Okay, good. Now, I want to fix this up because this is yucky. So I want to fix it up. So I want to write it as follows. This is equal to n. You know what? Let's put the n at the end. It's n. Okay, let's do this. 2 to the I times 3 to the I divided by 4 to the I. Okay, the 2's cancels out with that, you get 2 to the I. Okay, so you get 3 to the I divided by 2 over the I. So this becomes 3 over 2 to the I times n. What's 3 over 2? It's 1.5. So let's write it as 1.5 to the I times n. Okay, great. Now, let's find our eraser and let's sum it up. So I showed you what every single layer is equal to. Every single layer is equal to 1.5 to the n. That's it. Okay? Oh, by the way, we should do this. This is 2 to the 0 times 3 to the 0 divided by 4 to the 0. That's another way of saying n. Okay? So each one. So let's sum it up. You ready? This is equal to the sum. We're going to start from the 0, going to the height of the tree. What's the height of the tree? I equals 0 to log base 4 over 3. 4 over 3 of n. Okay, and each one is equal to 1.5 times n to the I. 1.5 to the I. Okay, great. Okay, this is equal to geometric sum here. The n goes to the front, and so this is equal to n times the sum. Well, okay, let's write it out again. I is equal to 0 of log base 4 over 3 of n of 1.5 to the I. Okay, now we use Mr. Geometric Series. Okay, we did this the same procedure over and over. We produce a sequence of trees. We add what's on each tree at each level. We do the ith level in general. We add them up. We use the geometric series. It's finished. Not hard at all. Okay, let's use Mr. Geometric Series. So this is n, don't forget that n, times, let's do this. This is 1.5 to the log base 4 over 3 of n plus 1, don't forget the plus 1, okay, that's geometric series, minus 1 divided by, 1.5 minus 1. What's 1.5 minus 1? 0.5. We get that. Okay, great. Let's work this out. When you divide by 0.5, that's like multiplying by 2. So this becomes 2, this is a half. So you put the 2. So this is 2n times what? Okie dokie. Okie dokie. Let's write it. This is 1.5 times log base 4 over 3 of n. Okay, the plus 1 means you're multiplying by 1.5 times 1.5 times 1.5. Okay, don't forget the minus 1. Okay, now that is everything's fine except I don't know how to do that. Okay, but we did it in class. Okay, let's just remember I did this rule in class because it's the only time. Because I knew about this example and I knew we'd see it here. So let's just remember this rule we had. We had the following. Damn. Don't move. We had the following rule. A to the log base b of c is equal to c to the log base b of a. The b stays the same, but you swap the a and the c. Okay, that's exactly what we have here. I don't know what log base 4 over 3 of n is, but I know that this whole thing is equal to, don't move, this is equal to, okay, ready? 2n times, now I'm going to bring the n down and the 1.5 up. The a and the c swap, so I get n to the log base 4 over 3 of 1.5 times 1.5 minus 1. Okay, now it's easy math. Notice that's a number. That's a whole real number. Log base 4 over 3 of 1.5 is a damn number. There's nothing to talk about. Okay. How do you figure out that number? Well, you go to your calculator. We saw how to do this before. Now let's just calculate it. You ready? I don't have that on my calculator. I don't have log base 4 over 3, but I do have log of 10. So let's do it. Log of 10 of 1.5 divided by log of 10 of 4 over 3 is equal to, I've got it, 1.409. That's a real number. Okay? And now we can plug that number in and we can get the whole thing. We get the final thing. So you ready? So this is equal to 2n times n to the, what did I say? 1.409, okay, times 1.5 minus 1. Okay, so this is equal to 1.409 times n, so this is 2 to the 2.409 times 1.5. What's 2 times 1.5? 2 times 1.5. That's just another way of saying 3. 1.5 times 2 is 3. Okay, minus 2 times n. Okay, and this is a member of theta of n to the 2.409. And we're finished. Okay, let's just review what we did. We started with the thing, we built a sequence of trees, we added up the trees, we saw that adding up each level of the tree is just this. Okay, the rest is just math. It's ugly math. We had to use this, we had to use this, but we did it. It's just ugly math of adding up this thing. We used the geometric series rule here, and we got it. Okay, so that takes care of that. So we did 3 baby examples and 3 big boy examples, big girl examples. We did 3 baby examples and 3 adult examples of these tree methods. Okay, very, very beautiful thing. Okay, let's take a minute and we'll do the next section. Okay, so this is the last section we're going to do in Chapter 4, Section 4.5, the Master Theorem to solve recurrences. Okay, this section you'll love. It's easy and it's straightforward, and you'll use it the rest of the semester. Every time you see it, you'll know this by heart, and you'll see it. And it's not hard. And we're not responsible for the proof. We're just doing the theorem. Okay, we're just stating the theorem. Okay, so a lot of the recurrences are of this form. You plug in n, you get a t of n divided by b. Okay, we had divided by 2, divided by 4 over 3. We had a lot of different examples. And then how many children does each one have? That's a. Okay, okay. And then you always add in a thing. Now, if you look at this, what we saw is what this b does is it determines the length of the tree, how high the tree is. Okay, and if you think of it, if b is small, tree is high or low. Okay, if b is small, that means you're dividing by a small number. Okay, then the tree is short. I think that's true. I'm sure that's true. If b is big, the tree is short. Oh no, right. If the tree is long, tall, it's tall. B is big, tree is short. Okay? Okay, if you're dividing out, you're going to get down to 1 very quickly. If you're dividing by this. Okay, as opposed to that, the A, how wide is the tree? Okay? Remember the first example, we had just a string that was very not wide, but then we started dealing with trees that had more than one child, etc., etc. How wide? Let's go through it. If A is a big number, the tree is very wide. If A is a small number, the tree is very small. Okay. Okay. Now these two numbers determine the tree. This determines what numbers are on the tree. Okay? What is actually on the tree. Okay. So what we do is as follows. Log base b, remember that tells you the size of the tree. You look at this number. Log base b of a. Again, this is I'm hand waving. I'm not giving you all the details. But basically, you look at this number and you look at this polynomial raised to this n raised to this polynomial, and you look at f of n. Okay. Now you're going to have two functions, this and this. You compare these functions, and the Master Theorem tells you what the closed form is by just looking at these two things. So it's very, very pretty. Okay? Very easy. Let's write out the Master Theorem. Okay? It's also easy to memorize. You're going to have to memorize just there's 3 cases, and there's a lot of symmetry here, and so you'll be able to memorize it with ease. Okay? The Master Theorem. And again, you're going to use it every day in this course. So it's important. Okay, there are three cases: case 1, case 2, case 3. Okay, and there are three possibilities. If f of n grows slower than O of log base b, O of n of log base b of a, leave me a little room here and I'll explain to you why. Okay, so it grows slower or the same size, or if f grows the same speed, that's theta, of n log base b of a. You don't have to leave me space here. If f of n grows faster than n log base b of a, leave me room here. Okay, so again, you're going to have those two things. This tells you kind of the size of the tree. The log base b of a, that's the size of the tree. B is the height of the tree. A is the width of the tree. Okay, and so we're going to compare what you're putting on the tree to the size of the tree. Okay, and you have three possibilities. Either it grows slower or equal to, or faster. Okay, then each one of them. So we're going to write comma, then, comma, then, comma, then. Okay, and what's the purpose of the Master Theorem? To give us closed forms, to give us functions for our recurrence formulas. T of n is equal to theta. Each one of them is going to tell us what T of n is equal to. Theta. T of n is equal to theta. Okay. Of n log base b of a. And down here it's f of n. Okay, so it's the thing that grows faster. It's always the thing that's faster. Okay, this grows slower than this, so we take the faster thing. This grows faster than this, so we take the faster thing. Okay, and in this case, it's n log b of a of times log of n. Okay, a little bit faster than this times that. Okay, good. Okay, so those are the three cases, and again, we're not responsible for the proof, but basically that's the way it works. And so a lot of times we're going to see these things. We're going to see recurrence formulas. We're going to pick out the A, we're going to pick out the B, we're going to find it, we're going to compare what's put on, and we're going to do it. Okay, the rest of this is just examples of worked out cases. So let's just work out some cases. Example, okay? T of n is equal to 5 times T of 2n over 3 plus n to the 2.5. Let's go through it. A is equal to 5. B is equal to, be careful. Be careful. It's not 2 over 3. Okay? Another way to write this is n over 3 over 2. So that's 3 over 2. Okay? Okay, now log base 3 over 2 of 5. This you need a calculator for. This you absolutely need a calculator for. That's equal to 3.96. Okay, and so we have now two things. F of n is equal to n to the 2.5. N to the log base b of a is equal to n to the 3.96. What grows? Does it grow faster, the same, or, I'm sorry, slower, the same, or faster? 2.5 is less than 3.96, therefore case 1. So we do case 1. Okay, and so we get out that T of n, that's this, example, this complicated example, we plug it into the Master Theorem, and we get that this is equal to theta of n to the 3.96. Done. Finished. Kaput. Nothing to it. Okay? Okay. The rest of the examples are pretty easy. I'm just going to do them a little bit quickly. But, and then for homework, there's 5 examples, and I gave you the answers to the homework. So, T of n is equal to 49. Each one has 49 children. T of n over 7 plus 23n squared. So let's go through this. A is equal to 49. B is equal to 7. That's 7. Okay. Log base b of a is equal to log base 7 of 49. What do you have to raise 7 to in order to get 49? Answer 2. 7 to the 2 is equal to 49. Okay, and so what we have is, we have 23n squared, that's f of n, and log n to the log base b of a is equal to n squared. What grows faster? Answer, they grow at the same speed. They grow at the same speed, that means it's case 2, and so your final result is, this is second case, so T of n is equal to n squared, theta of n squared times log of n. Okay, let's do another example. Okay, that's another example. T of n is equal to 9, T of n over 3 plus n to the third divided by 82. Okay, I made up these examples, nothing complicated here. Maybe I took them from the book, I don't remember. A is equal to 9, B is equal to 3. Okay, log base b of a is equal to, what do you have to raise 3 to in order to get 9? Answer is 2. So this is, so basically we look at n squared, and here we look at n to the third. F of n is equal to n to the third divided by 82. F grows faster, so this is case 3, okay, and basically T of n is equal to theta of n to the third. That's it. That's the third case. Okay, one more example, just for completeness. Okay, T of n is equal to 2 times T of 3n over 5 plus n squared. Okay, the only reason I'm doing this example is to calculate the b. A is equal to 2, b is equal to, okay, not 3 over 5, but 5 over 3. Okay, log base b of a is equal to 1.359. You need a calculator for that. Okay, and so what grows faster? N to the 1.349 or n squared? Answer, n squared grows faster. Okay, and conclusion, that's a case 3. So T of n is equal to n squared. That's it. Theta of n squared. Okay, so that's the end of chapter 4. That's the end of the preliminaries. Okay, notice we didn't do any massive algorithms. We just spoke in general about what recursion's all about, and we solved recurrence formulas. That's what we did today. Okay, these last 2 sections. The rest of the chapter is proofs of it, and that's fine. You can look through it. You'll see it's made out of a lot of trees. You have a lot of trees. You talk about the width of the trees. You talk about the height of the trees. Exactly what the intuition tells you to do. Okay? Okay. Now, Chapter 5 we skip. It's about probabilistic algorithms. It's very nice out. We just don't have time for it. Okay, and now we start going through it. 6, 7, and 8 is about sorting and things like that. So, and then every single chapter we do is different stuff. Okay, so I hope you enjoyed it. Take care.